Good morning, everyone. I'm Dr. S.K. Singh, holding a PhD, and I'm excited to welcome you all today. We will be discussing potency or assay calculation of API, which is a crucial aspect in pharmaceutical analysis. In this presentation, I will guide you through the fundamental concepts, methods, and best practices involved in determining API potency. We'll cover the key techniques, calculations, and some practical tips to ensure accuracy. So, let's get started and explore this important topic together. Potency calculation of active pharmaceutical ingredients is one of the most common activities that pharmacists perform daily in the pharmaceutical industry. It's a critical step to ensure the quality and efficacy of the medication. However, it's interesting to note that many pharmaceutical professionals are not fully aware of how to accurately calculate the potency or assay of an API. Now, let's talk about moisture content. The amount of moisture in the API is checked through the certificate of analysis for that specific batch. Adjusting for moisture is essential because it can affect the drug's efficacy. If there's excess moisture, it can dilute the active ingredient, which is why precise measurement and correction are so important. So, what exactly is API? API stands for active pharmaceutical ingredient, and it's the component responsible for the therapeutic or pharmacological activity of the drug. It's the element that actually cures, treats, or prevents the disease. All other ingredients in the formulation, called excipients, don't have any pharmacological effect. They're just there to aid in manufacturing, stability, or delivery. Because the API is the active agent, its quantity must be measured precisely. The dosage should always match what's claimed on the label to ensure safety and effectiveness. When calculating the potency of an API, we consider a few key factors. First is the moisture content we just discussed. Second, we need to account for any salt removal or factor adjustments. This ensures that the actual amount of active substance is accurately represented in the calculation. In summary, understanding these factors helps us maintain the quality and consistency of pharmaceutical products, which is the overarching goal of our work in this industry. Let's talk about salt removal or factor adjustment. Some active pharmaceutical ingredients like metformin HCl are used in salt form, while others, such as sitagliptin phosphate, are used without the salt, meaning we remove the phosphate factor from sitagliptin. So the key question here is, how do we know when to use an API in salt form and when to use it without the salt? The answer lies in reading the label claim carefully. If the label states that each tablet contains sitagliptin phosphate, then we don't need to remove the salt form because that's the active form specified. But if the label says each tablet contains sitagliptin as phosphate, that indicates we need to remove the salt form from the API before formulation. It's important to understand that many APIs provide their pharmacological effect in salt form, which can enhance properties like solubility or dissolution. On the other hand, some APIs are effective without the salt. In those cases, the salt acts mainly as a carrier, not necessarily contributing to the therapeutic effect. So always check the label claim carefully. It guides us whether to retain or remove the salt form. This is crucial for ensuring the correct dosage and activity of the active ingredient in the final product. Let's explore how to adjust from 97% to a perfect 100%. To do this, we need to add a 3% extra API to compensate for moisture content, or MC. Alternatively, we can use a specific factor to calculate the API. This factor is 100 divided by the assay minus the MC. So in our case, it's 100 divided by 100 minus 3, which equals 1.03. This 1.03 is our moisture content compensation factor. Now, how do we adjust the MC of the API? Typically, we assume 100% API, but since we have 3% moisture, we need to compensate for that. We do this by calculating assay minus MC divided by 100, then multiplied by 100. Putting it into the formula, it looks like this. 97 divided by 100, then multiplied by 100, which gives us 97%. So our actual API, after accounting for moisture, is 97%. Let's consider an example to clarify this. Suppose we have an API with an assay of 100%, and the certificate of analysis claims it has 3% moisture content. We use this method to accurately determine the true potency, ensuring our measurements are precise and reliable. Let's break down what this slide is telling us about moisture content, or MC, in simple terms. In the statement above, it mentions 4% moisture content along with the API. What does that mean exactly? Well, if we have 50 kilograms of API and it contains 4% moisture, then 4% of that 50 kilograms is actually moisture. Calculating that, 4% of 50 kg is 2 kg. This means we need to add an extra 2 kg to compensate for the moisture. So, instead of just 50 kg, we're effectively working with 52 kg of API when moisture is included. In other words, 52 kg of API with 4% moisture content is equivalent to 50 kg of pure API without moisture. Now, let's look at an example to make this clearer. Suppose a pharmaceutical company uses 50 kg of API to produce 100,000 tablets. Each tablet contains 500 mg of API, and the API assay is 100%. The question is, how much moisture content compensation do we need here? To find out, we use the formula 100 divided by assay minus MC, so 100 divided by 100 minus 4, which equals 1.04. Then we multiply this factor, 1.04, by the amount of API in kilograms. So 50 kg times 1.04 equals 52 kg. Alternatively, you can think of it as adding 4% extra to the original amount. 50 kg times 4 divided by 100 equals 2 kg. Adding that to the original 50 kg, we get 52 kg. So the key takeaway here is that when moisture is present, we need to adjust our API quantity accordingly, either by calculating the factor or by simply adding the extra weight. This ensures we account for moisture content accurately in our formulations and manufacturing processes. Let's talk about how moisture content actually affects our assay results. If we calculate the assay without considering moisture and dispense 50 kilograms of API with a 100% assay, things might seem straightforward. But when moisture is present, that 50 kg isn't just pure API. In this example, 2 kilograms of that weight are moisture. So the actual API content is 50 minus 2, which gives us 48 kg. Now, if we look at the assay based on this, it becomes 96% because we're comparing 48 kg of pure API to the original 50 kg. Now, if we include moisture compensation before dispensing, we're actually dispensing 52 kg instead of 50. That's because we're accounting for the moisture content, which means we're giving 4% more API than we would without compensating for moisture. And if we recalculate the assay with this adjustment, the assay of that 52 kg becomes 104%. The 4% over 100% reflects the moisture correction, and the 100% represents the actual API content. To put this into perspective with individual tablets, if we have 50 kg of API at 100% assay, each tablet containing 500 mg would actually have 500 mg of API, but 4% of that is moisture. Calculating that, 500 mg times 4 divided by 100 gives us 20 mg of moisture per tablet. This means each tablet contains 20 mg less of pure API than we might think at first glance. So the assay for each tablet is actually lower than 100%. In essence, moisture can significantly impact the measured assay, and accounting for it ensures we dispense and evaluate the correct amount of active ingredient. On this slide, we're looking at how moisture content affects the assay of our tablets. First, notice that our tablet contains 20 milligrams less of the active pharmaceutical ingredient, or API, than the label claim. For example, if the label states 500 milligrams and the actual content is 480 milligrams, we need to adjust for that difference. To calculate the assay of a tablet with 480 milligrams of API, we use this formula: 100 divided by 500 multiplied by 480, which gives us 96%. This means the actual API is at 96% of the stated amount. Since we want the tablet to still meet the label claim, we add a 4% extra API to compensate for moisture or other losses. We do this by multiplying 500 milligrams by 1.04, giving us 520 milligrams. Now, if we calculate the assay for this adjusted amount, we get 100 divided by 500 times 520, which equals 104%. Here, the 4% overage accounts for moisture content, and the remaining 100% reflects the assay of the API itself. Moving on, let's talk about salt removal or factor adjustment. Sometimes, the pharmacological effect is due to the API with salt, like sitagliptin phosphate, or without salt. To adjust for this, we use the molecular weight ratio of the API with salt to the API without salt. This helps us accurately determine the actual API content in our formulation, ensuring our measurements are precise and reliable. Let's look at this example to understand it better. The label claim on a tablet states that each tablet contains sitagliptin phosphate 50 milligrams. Now, in the pharmaceutical industry, we often work with large quantities. For instance, 10 kilograms of sitagliptin phosphate are used to produce 200,000 tablets. Since we know the strength of each tablet is 50 milligrams, the key question is, how much sitagliptin phosphate is actually in one tablet? To figure this out, the first step is to convert those 10 kilograms into milligrams, because that's the unit we're working with for the tablets. So, 10 kilograms equals 10,000 grams, and since there are 1,000 milligrams in a gram, we multiply 10,000 grams by 1,000, which gives us 10 million milligrams. Next, we divide this total amount of sitagliptin phosphate by the number of tablets produced, which is 200,000. Doing that calculation, 10 million milligrams divided by 200,000 tablets gives us 50 milligrams per tablet. This confirms that each tablet contains 50 milligrams of sitagliptin phosphate, aligning perfectly with the label claim. Now, to put it another way, if the label states each tablet contains 50 mg of sitagliptin as phosphate, this calculation shows us how the total raw material correlates with the individual dosage. So, the key takeaway here is understanding the relationship between total raw material used in manufacturing and the amount present in each dosage form. This example helps us see how the batch size and total raw material translate into the strength of a single tablet, which is essential for quality control and ensuring consistency in pharmaceutical production. Let's start by figuring out how much sitagliptin phosphate is in one tablet. First, we need to convert kilograms into milligrams. So 10 kilograms times 1,000 gives us 10,000 grams. Then, 10,000 grams times 1,000 equals 10 million milligrams. Next, we divide this total by the batch size, which is 200,000 tablets. When we do that, we get 50 milligrams per tablet. Now, here's an important point. The 50 mg we calculated is for sitagliptin phosphate, but what we actually need is just sitagliptin, not the phosphate part. Since the pharmacological effect comes from sitagliptin itself, we have to remove the phosphate conceptually. But how do we do that? Well, physically, we can't easily separate phosphate from sitagliptin in the manufacturing process. So instead, we add a compensation factor, often related to moisture content or other factors, to account for the phosphate. This means we include extra weight of the active ingredient in the formulation to ensure the correct dose of sitagliptin. This is a key concept because it helps us understand how the actual dose is adjusted during formulation to target the active compound, not just the salt form. Let's walk through the calculation method for salt removal or factor adjustment. We start by using the molecular weight of sitagliptin with phosphate, which is 505.31 grams per mole, and divide it by the molecular weight of sitagliptin without phosphate, which is 407.31 grams per mole. When we do that calculation, 505.31 divided by 407.31, it equals approximately 1.24. This number, 1.24, is our factor for salt removal or adjustment. Now, how do we use this factor? Well, we multiply it by the total amount of API in kilograms or by the strength of each individual tablet. For example, if we have 10 kilograms, multiplying by 1.24 gives us 12.4 kilograms. Or, if each tablet has a strength of 50 milligrams, multiplying that by 1.24 results in 62 milligrams per tablet. From this, it's clear that to remove phosphate from sitagliptin, we need to use 12.4 kilograms of sitagliptin phosphate instead of just 10 kilograms. To understand what this means in terms of tablet content, we convert 12.4 kilograms into milligrams, multiply by 1,000 to get grams, then again by 1,000 to get milligrams, and finally divide by the number of tablets or the total weight to find out how much sitagliptin phosphate corresponds to 62 milligrams of sitagliptin. In the label, it states that each tablet contains 62 milligrams of sitagliptin phosphate, which is equivalent to 50 milligrams of sitagliptin. So, what this tells us is that approximately 12 milligrams of phosphate correspond to 50 milligrams of sitagliptin. Now, moving on to how we calculate the percentage of API in a formulation. Say we have a tablet product, Z, which contains sitagliptin phosphate with a strength of 25 milligrams per tablet. The manufacturing order confirms that each tablet contains 25 milligrams of sitagliptin phosphate. To find the percentage of the active pharmaceutical ingredient, or API, in this formulation, we need to relate the amount of sitagliptin phosphate to the total weight of the tablet. Since the label claim is 25 milligrams of sitagliptin phosphate, and we know the molecular weight, we can determine how much sitagliptin is present, and then calculate its percentage relative to the total tablet weight. This process helps us understand the formulation's potency and ensures it meets the specified active ingredient content. Always remember, these calculations are crucial for quality control and regulatory compliance in pharmaceutical manufacturing. Now let's look at how we determine the percentage of the active pharmaceutical ingredient, or API, in this formulation. First, we start with the total weight, which is 20 kilograms. The tablet weight, as given, is 100 milligrams. The key question here is, how do we find the percentage of API in this batch? To do that, we follow a specific procedure. First, we need to convert the total weight of the API from kilograms into milligrams. Since there are 1,000,000 milligrams in a kilogram, we multiply 20 kilograms by 1,000,000. That gives us 20 million milligrams. For simplicity, the slide shows it as 6.324 times 1,000,000, which results in 6,324,000 milligrams. Next, we divide this total milligram amount by the batch size, which is 200,000 tablets. So, we take our 6,324,000 milligrams and divide it by 200,000. This calculation tells us the amount of API per tablet in milligrams, which comes out to approximately 31.62 milligrams. Finally, to find the percentage of API in one tablet, we divide this amount by the tablet strength, which is 25 milligrams. So, 31.62 divided by 25 equals roughly 1.2648. This percentage indicates how much API is present relative to the tablet's strength, helping us understand the formulation's potency. And just to tie it all together, the manufacturing order details specify the product name as ABC25mg, with a batch number 1235 and a batch size of 200,000 tablets. These details are crucial for traceability and quality control in the manufacturing process. In the results section, we see that the API percentage is calculated to be 102%. This indicates that, after adjustments, the active pharmaceutical ingredient in our product slightly exceeds the labeled amount, which is an important point for quality control. Moving on to the conclusion, it's essential to remember that active pharmaceutical ingredients, or APIs, are always used after proper adjustments. Specifically, we need to account for moisture content and any salt removal to ensure the API measurement is accurate and consistent. Now, regarding the manufacturing order, we have a specific calculation to remove salt based on the label claim. We use the molecular weights. The molecular weight of sitagliptin with phosphate divided by the molecular weight of sitagliptin without phosphate. So we take 505.31 grams per mole and divide it by 407.31 grams per mole, which gives us approximately 1.24. Next, we divide this value, 1.2648, by 1.24, resulting in about 1.02. Finally, to express this as a percentage, we multiply 1.02 by 100, which gives us 102%. This calculation confirms our API content after adjustments is 102%, aligning with the overall formulation requirements. It highlights the importance of these adjustments to ensure our product meets specifications reliably. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional information you might need. Thank you so much for your time and attention today. If there's anything else you need, feel free to contact us. Once again, thank you for being with us and for your interest.